welcome everybody to our HPC IC Spack tutorial. We do these every year for Lawrence Livermore open source projects, and this is a 2-day tutorial. It's a full day tutorial, just like we do at supercomputing, spread over 2 days. So I hope you enjoy it. And Greg's already given instructions, so I'm going to get started. So the presenters today are me. I'm Todd Gamblin from Lawrence Livermore. I created the Spack project back in 2013. It's come a long way since then. Alec and Greg are both developers at Livermore. Greg's been working on the Spack project since around 2015, and Alec has just come on board in the last few years to Livermore and has started working on the project as well. So we're all core developers on the project and can help answer questions in Slack and on the WebEx while the tutorial is going on. So definitely feel free to ask. We generally prefer questions in Slack just because the threading is better, like Greg said. So if you can go to slack.spack.io and join the tutorial channel there, then that's probably the best place to ask. But the WebEx chat is fine too if you can't pull that off. All right. Like Greg said, all the tutorial materials are on spacktutorial.readthedocs.io or rtfd.io. The page that you should be looking at looks like this, and you should see slides are available there. That's the ones I'm presenting now. All the different sections of the tutorial there, and basically what we're going to do is follow along with scripts for each section that we're going to do today. And so there's an initial presentation with some slides, and then the various sections are coming right out of these tutorial scripts. So if you fall behind, you can follow along there. Or if you want to just do the tutorial later at home, again, or review sections, it's all available for you. This is going to be labeled with the HPC IC 24 version in the version list on Read the Docs if you want to get back to this specific tutorial. And we are recording, so the recording of this tutorial is going to be available there afterwards. I don't know how long it generally takes to get it processed from WebEx. We're going to have to release the video, but we're going to post it there so that we have an updated video once it's available. So, and you can see the URLs are down here as well. So while I'm going along in the slides, you can follow them there. Okay. And I think someone asked what channel in Slack. It's the tutorial channel in Slack. So that's where. So see, join the tutorial channel right there. Right. Okay. For the tutorial, we are going to have VM instances available in Amazon. And they are set up so that all the installations go fast. Generally, when you use Spack, it's going to build some stuff from source. And so we've set it up to accelerate that by using binaries for the tutorial. And what you need to do is go to bit.ly/spackvms. You can use this QR code, although it seems kind of silly if you're on your own computer right now. And there's a spreadsheet that looks like this. Basically, if something is going to sell, don't overwrite it. That's someone who's claimed an instance. There's going to be IP addresses for instances over here on the left. And then these are usernames. So each of the instances that you can log into has 10 different users, and just put your name in a cell. And then if you put your name in this cell, you're a Spack2 on 35.91.36.120. And you can SSH Spack2 at that IP, and your password will be Spack2 as well. So we're going to show this again before we start the hands-on section, but you can go ahead and get started by going to this URL and messing with the Google Sheet now. So, and then I guess Alec and Greg, do we have enough VMs for all the people who showed up today, or do I guess keep an eye on it in case it starts filling up, and we'll provision some more
on it.
Okay, awesome. Okay. This is the agenda for what we're going to talk about today. I'm going to do an intro, and then Alec is going to talk about basics of using Spack. I'm going to come back for the concept section to just sort of talk about the key concepts behind the basic user interface that we show in the basic section. We're going to have a 30-minute break in an hour and a half from now or so. And then we're going to cover Spack environments, which are sort of a workflow and reproducibility tool. And configuration after the break. And then we end today at 11:30 a.m. I guess you can have lunch. And then we'll start again tomorrow at 8 a.m. And we'll do software stacks. This is the one to come to if you want to learn about how you might deploy Spack at an HPC facility. So if you're trying to build a software stack for users, you would want to come to the software stack section. And then packaging is how to create your own Spack packages. So we're going to go through a really simple example of how to do that and get you started on contributing. There's another break after that, and then we're going to talk about developer workflows, how people use Spack to do development. We're going to talk about how to set up mirrors and binary caches. Specifically, we're going to look at how to use an OCI registry as a binary mirror for a Spack workflow. So there's a cool example in the tutorial for that, and then scripting for folks who want to learn a little bit about how to use the Spack internal APIs, and then we're done. So that's the full schedule. All right. Any questions on logistics before I get started with the intro? Right. I guess just ask them in the chat, and then Greg and Alex will take care of them. Right. So we build codes from hundreds of small complex pieces, and there's a paper from October 2003 called "Why Johnny Can't Build" by some folks at Livermore who they had built modular codes. They had bought into the whole object-oriented design philosophy. And they were frustrated because just when they had the design of the codes done, it seemed like the reuse of the codes was actually foundering on people trying to build them. So the nuts and bolts problems outside the software itself. We use component-based software development all over the place. And in fact, I think there's been different forms of this. There's been reusing routines. There's been reusing objects. And I think the latest form of this is reusing packaging or packages in the open source world. And that's where reuse really took off, where people are using hundreds of libraries from others. There are lots of good reasons to do this. Teams have to use each other's work to get stuff done as quickly as they need to today. And it ends up that you write less code and meet deliverables faster. However, now you're in the job of integrator. You have to make sure that all the components that you're using are up to date, that they're secure, that they work together, that they're consistent, and you have to vet the components themselves. And if things go wrong, at build time, maybe the whole puzzle just doesn't fit together. But if they go wrong subtly at runtime, maybe something horrible goes wrong, maybe silently. And so it's really important to make sure that your whole software stack is built in a consistent way, and that you can manage that over time. And that's becoming difficult. Spack's designed for scientific codes, and these rely on huge numbers of dependency libraries. So if you look at a simple domain-specific library like MFEM, it's for higher order finite elements. A basic configuration of MFEM is still going to be 31 different packages. There's MFEM itself, there's some solvers in here, there's IO libraries and so on. And there's 69 different dependency relationships just in that configuration. If you look at AI tools, they run in the realm of 71 different packages, lots of Python in there, other sorts of libraries for doing communication over the network, and other aspects. This is LBAN. It's one of Livermore's AI tools. It's similar in size to TensorFlow or PyTorch. So they all kind of run about this size. And then in other ecosystems like R, or even like JavaScript, there are huge numbers of packages. So this is R Condob. It's 179 different packages. And so you can see here's R Condob, here's all of its R dependencies up here. Here's R, this little node down here. And then here's all the native dependencies of R. These things get to be very large. There are bigger stacks even than that. Under the Exascale Computing Project, which ended last year, there was the Extreme Scale Scientific Software Stack, or E4S. And that was an effort of all of DOE to put together a stack for exascale computers, and it's around 120 packages at this point. And to build all of that, to build the 120 packages that ECP cared about, there's 600 other dependency libraries underneath there. And integrating all of that manually is just not feasible, especially for 3 different machine architectures. And so we need tools to manage software at this scale. Even proprietary codes use lots of open source. So this is Aries. It's a multiphysics code used for ICF and other stuff at Lawrence Livermore. The pink nodes here are Livermore internal libraries. And so you've got components that are developed internal to Livermore that we don't distribute anywhere. The yellow components here are open source components developed at Livermore. So they're ones that are developed mainly by Livermore staff, but that are open source. And then the blue stuff is external open source. So you can see that 83 packages out of this code, the vast majority of them are open source. And there are very few codes, even proprietary ones today, that don't rely on a ton of open source packages that we have to integrate. Out in the open source ecosystem, there are lots of different package managers. Many of the ecosystems make assumptions that sort of limit what they can do with their integration. And so one of those is that there's a one-to-one relationship between source code and binaries. So you've got canonical source code, you build it one way, you get one binary that's maybe reproducible, like in Debian. But the goal of that is to ensure that the binary is as portable as possible and that it can run in lots of different places. What that typically means is that it's not optimized. And so to get really good optimization, you need to optimize for a specific machine, a specific architecture, a specific GPU. And so most distributions are shipping unoptimized binaries that are built for sort of the base instruction set on the platform, and not leveraging all the vector operations that would get you a good performance for numerical stuff. And then the other assumption that comes up frequently is that most package managers at the OS level are assuming one compiler and one set of runtime libraries. And so there's just one tool chain to build the whole stack. And it's usually the system compiler. Everything is using the same, say, live standard C++. And integrating with that, you're limited to whatever the system compiler is. There are things like dev toolsets in RHEL, and SUSE has an equivalent. But again, you're limited on the system to one version of that library from the whole system. And so you don't get the freedom to use multiple software stacks that maybe have dependencies on different versions of libraries. And so you're pretty much on your own and have to build your own stuff when you get to that point. In HPC, we build applications that violate a ton of those assumptions. And that's why historically the code distribution in HPC was sourced. People would ship tarballs. Others would build the tarballs by hand on their machines. And you would probably build lots of different variants of the same package. So you'd build different versions of the same library in different directories. And if you tried to build that in an OS package manager, that might cause a conflict because you can't have two versions of the same library. You'd have code that's optimized for the processor and the GPU. So again, you have very specific instructions in there, very specific support for GPU architectures. And at the same time that you're building all this stuff from source, you rely heavily on system packages, because at most HPC centers, you've got admins who are deploying system libraries like MPI, like maybe the system CUDA, system ROCm, and you need to rely on those because they are tuned for the machine. They're configured in a way that the admins know to work well at the site for its network or whatever, and you need to use the optimized libraries that come with the machines, and they may be proprietary as well. So this is sort of a mess from a build perspective because you have to put lots of different components together, both from source and from binaries. And there are lots of different languages. So C, C++, Fortran, Python, Lua, others, all in the same ecosystem. And the architectures that you need to support are very diverse. So you've got anything from a Power 9 system with NVIDIA GPUs over to like ARM systems, Intel GPUs, AMD GPUs, and so on. The ecosystem is becoming much more diverse. Containers are great. They provide a way to reproduce and distribute something that you've built already, but someone has to build a container. And often in HPC, you want to build a container that's optimized for the platform. So again, you want to use an optimized instruction set. You want to build for a particular GPU. Just using the OS package manager inside the container isn't sufficient for getting all the diversity that we need in HPC. And so you may need to rebuild the same container many different times to support lots of different hosts. It's not clear that you can build one that's portable across all facilities that still gets really good performance. And so you need something more flexible to build the containers. So that's what we're going to talk about today. Spack is a package manager for HPC. It's designed to enable software distribution for HPC by automating the build and installation of scientific software. The way that we do that to meet all of the crazy number of requirements that HPC imposes on us is that the packages in Spack are parameterized. So we don't just ship packages, we ship recipes that have lots of parameters so that users can easily tweak and tune their configuration for a particular architecture. So we're gonna, you just clone it from GitHub and you can start installing right away. We have a simple syntax that enables lots of different complex installs. You can specify versions, compilers, flags, and so on. We'll get into the details of that later. But the idea is really to provide the flexibility that's needed for HPC so that people can tailor things to their use case while also making things as easy as we can make it compared to regular package managers. And then in addition to that, Spack doesn't just do installation, it also can generate modules for your system. So if you're used to environment modules, we can generate those for users. It lets you generate environments kind of like Conda or VirtualEnv, but with a manifest and a lock file for reproducibility. And there are lots of developer and DevOps features built on Spack that we'll talk a little bit about in the tutorial today. It also supports binary packaging. So what we're really trying to do with Spack is make the sort of distinction between source and binaries seamless, so that you could say reuse a bunch of binaries and build source things on top of them. So that's the goal that we're going for. We have a number of things that are sort of moving in that direction, despite having started as a build from source package manager. So what is a package manager? When we first started giving these tutorials, I think they were much less common, and a lot of people asked us, does Spack replace CMaker Auto Tools? I just moved to CMaker Auto Tools, and now what do? I have to move to this new build system? No, it's not. It's not replacing those things. Spack manages dependencies, and if you think about projects that people work on, open source projects or what we call a package, there's sort of three different types of build systems that you want to think about. There's low-level build systems like Make and Ninja that really manage dependencies between files and converting, say, a C file into an O file. There's high-level build systems like CMake and Auto Tools, which add a lot of abstractions sort of at the project level. They handle things like the distinctions between shared libraries on different operating systems. They generate make files or Ninja files and so on. They have higher-level dependency abstractions for the libraries in one program or one library. But they're really managing a single project. So a single thing in a single repo that one team works on that's tightly connected. And package managers are really for managing an ecosystem of software. So it's not just your project, but it might be your project and all of its dependencies, or it might be all the dependencies for a software ecosystem, all of the open source packages that people typically leverage in a particular area. And what it's doing is it's driving the package level build systems or installing binaries to ensure consistency and compatibility among all the things that you use together. And it's managing dependency relationships so that if you say, I want that package like HDF5, it knows to bring in all the dependencies of HDF5 so that you don't have to think about that. You think about the sort of root package that you depend on and not all of its dependencies. And it stores community knowledge. So all this build stuff is very hard to learn without a lot of experience and a lot of banging your head against the wall and seeing build errors and so on. And so coming up with the magic configure arguments for a package or understanding how each package's build system was designed can be pretty complicated, especially if you're integrating tens or hundreds of packages. So a package manager serves to store a lot of community knowledge about those packages in a common place. So the recipes, how they should, how things should change if certain parameters change, and so on. And we'll get into that with more details on Spack. Spack's targeted for a lot of different audiences, so we've tried to make it very flexible. It's targeted at end users of HPC software, so if you want to get on a machine, or if you want to just get on your laptop and run some simulation or maybe AI tool, you can install that and run it just by using Spack as a normal end user. It's made for application teams who may maintain their own stack of packages, so they may have a lot of third-party dependency libraries they want to manage. So Spack's designed to ease that task. And it's designed for people who want to have people use their software. So if you have a package that you want everyone to be able to use easily, then you could consider putting it in Spack. Or if some package that you use frequently, you'd like other people to be able to use it easily, you could consider making a package recipe for it in Spack and making it available to lots of people that way. And then finally, Spack's designed for user support teams at HPC centers, people who deploy software for lots of users. And so it's designed to do tons of builds, to do combinatorial builds with different MPIs, different compilers, and so on, and to generate the modules that go along with that. So there's lots of different use cases. We are officially a Linux Foundation project now. So Spack is not owned, the Spack trademark is not owned by Lawrence Livermore National Laboratory or any of the other contributors. It's owned by Linux Foundation. And what that means essentially is that there's no one can say, okay, you can't use the Spack name, you can't use the or we're going to change access to the Spack code. It's open, it's out there, it's for anyone to use. It's licensed Apache 2.0 or MIT, and it even has its own legal entity, so we can have things like legal agreements with people for distributing binaries and stuff like that. We are forming the technical steering committee for the project, and so that's going to be an open meeting. We currently have a core developer meeting that's not exactly closed, but we don't advertise it, and so we're going to have a public technical steering committee meeting as well soon. And so we're working on project governance as we stand this up. We're part of the High Performance Software Foundation, which is also new this year. So if you want more information about that, go to hpsf.io. Right. And Spack has come a long way since it started back in 2013. I started working on this to simplify life for a grad student who had a lot of dependencies on the BlueGNL system at Livermore back then. And this is showing over time the number of lines of code that were contributed to the project. And so you can see that the contributions to Spack have come from all over the place. Around 2015, when we presented this at Supercomputing, we started getting contributors. And so now, hundreds of organizations have contributed to Spack. We have users all around the world who are contributing and using the tool. And this is based on contributions to our documentation site. So I don't really know how accurate these numbers are in terms of like total users. We have 5,000 or 6,000 monthly active users on the documentation site. So it gets a lot of use. And that's helpful because all these folks who are contributing to the package ecosystem are really helping to maintain the project. We could not manage the now over 8,000 packages in Spack ourselves without help from all these other organizations, from experts who know the software systems and can contribute recipes for them. And so one of the things that we try really hard to do is make sure that we keep getting contributions to the project. So we give tutorials like this. We try to increase the user base and increase the contributor base to make sure that we can sustain this over time. Spack's getting a lot of use in industry as well. AWS helps us out with CI, as does the University of Oregon. Google is also helping us with CI, and AWS and Google are both using Spack in their cloud cluster solution. So AWS has Parallel Cluster, Google has HPC Toolkit. Both of those have Spack integration and use Spack to deploy software. Other vendors contribute changes to packages. AMD has contributed a whole bunch of stuff to the ROCm ecosystem within Spack, modeling all 50 or so ROCm packages. And HPE, Intel, NVIDIA, Fujitsu, Riken, and ARM are all contributing to Spack packages for their machines. So we're really happy to have gotten this level of engagement from companies who help us maintain the package ecosystem as well. It's pretty busy out there in the Spack project. In a month, we probably typically merge 300 to 400 pull requests, and most of that is to package recipes, but we're also constantly working on the core. And so the core tool evolves over time as well. And you can see down here that there's a pretty long tail of users who help us out with the project. So really happy to have that. We released the latest version of Spack 0.22 back in May, and we did one bug fix update to it. The big feature here is compiler dependencies. We won't get into all the details of the release, but if you're interested in learning more about things that are going on in recent Spack versions, you can find full release notes for these things at github.com on the releases link there. So it's github.com/Spack releases. And there's different tags under there, but you can get to the full list with just the releases link. So check that out. And this is not the only HPC package manager that's out there. There are other things that people use. Spack is probably the most used one, but it was inspired in large part by Nix, which is a functional package manager. Spack adds a lot of parameterization and a lot of flexibility on top of sort of the rigid packages in Nix. Geeks is similar to Nix and has a number of people doing HPC work within it. And then Spack's package interface was really inspired by Homebrew packages, the way that each package is a class. We'll see something about that later on in this tutorial. These are built from source package managers. You may be familiar with them. Gen 2 is kind of the original one for building a whole Linux distribution from scratch. And then EasyBuild is probably the biggest other tool in the HPC space. I'd say it's more of an installer than a package manager, but it also has a lot of recipes. You could check that out if you're interested in alternatives. And then Conda, Mamba, and Pixie are all package managers for the Conda ecosystem and for Conda Forge. So you can check these out. These are mostly binary package managers. And the source build for Conda, Mamba, and Pixie is sort of separate. And so if you want source and binary integration, Spack is probably a better bet for you on that. All right. So any questions on that stuff? Or I guess if you have questions, ask them in the chat. I think we got to get to the hands-on section. I'm going to put the hands-on link up here again. And I guess hand it over to Greg or hand it over to Alex so that he can do the basics section. So take it away, Alec.
Sweet. So once you've got a VM instance, you can SSH into it with Spack and then the number based off of the different column that you end up on the sheet. This guy. Once you guys all have a VM and you're set up and you log in, you'll get into your Spack user. The first thing we're going to do is go ahead and download Spack or clone Spack for ourselves. And to start that, just because this is really big, I'm going to reset my terminal to be a little bit smaller of a prompt, but you guys can just log in and start working. The first thing we're going to do is git clone. We're going to do a depth of 100 for this tutorial, but you could just do the full thing. This is just to speed it up a little bit. And then we're going to be working off of the 022 branch here. And then it's github.com/spack.get.
You missed dash branch equals.
Oh, yes, I did. Thank you for the heads up. Sweet. And then we're going to go ahead and clone that. You can clone it into /Spack inside of the home directory for your user. Once we do that, we are going to cd into that Spack directory, and then we'll go ahead and load Spack into our environment. Because if you tell right now, if you were to run Spack, we're going to get no Spack command found. So you source this script, which is under share Spack, and then setup env. At this point, we go ahead and run Spack. You'll see that it's now loaded into our environment, and we've got a whole bunch of Spack commands available to us. One of those commands, the very first one that we're going to look at today, is called Spack list. Spack list is going to show you all of the available packages inside of Spack. So if we just do Spack list to start, this is going to take a couple of minutes or a couple of seconds to a minute to populate the initial caches, but future runs of Spack list will be much faster than this. But we will go ahead here, and after we get everything printed out here, you can also pass the names of packages. So you can really use Spack list like you're searching for a package inside of Spack if you want to see if someone has already gone and created the package for it and imported the build instructions for us to be able to package it inside of Spack. So you can run Spack list, and this is showing down here a blob or a simplified regular expression. So that we're looking for all of the packages that start with pi. Pi is the prefix that we use for a bunch of the Python packages inside of the Spack ecosystem. There are other package ecosystems that conform to a similar naming convention. A bunch of the R packages start with R and dash. So yeah, and then you can obviously just get at the name of a package or the name of a partial package here if you were looking for one specific system. So still creating the initial caches here, which is taking a quick second. I guess there's lots of people also on this VM. Probably could have made them a little bit bigger or something. So we'll take that into note. Okay, there we go. So we currently have, or in the release v22.1, we have 7,993 packages inside of Spack at the moment. And inside of develop, which is kind of our rolling release, we are up above 8,000 packages now. So there's a very good chance this piece of scientific software that you want is inside of Spack. So we'll go ahead and rerun that again and can show you that after you generate that cache the first time, it's much faster upon subsequent runs. And if we wanted to look at that, do a Spack list and look for everything that starts with pi, you can go ahead and do something like that. You can see that we have 2,556 Python packages currently in Spack. Building on top of Spack list, let's say that you've searched out, you found a package that you want to install. You're going to use obviously or nicely named the Spack install command. So here, let's do a Spack install on gmake. We press enter there. We'll see that we're going and fetching some stuff from the initial build cache to bootstrap Klingo for ourselves, which is our logic solver. We'll get into that a little bit later. And then we're going ahead and installing the GCC runtime in gmake itself. We'll talk a little bit about the GCC runtimes and how we model compilers here in a minute. But needless to say that in V22 and some of the more recent versions of Spack, so if you've taken this tutorial a couple years ago and didn't see GCC runtime, that is something new. We now model the compiler environments for folks. So great, and now we've gone and installed our package. So you can see that we installed gmake at version 4.4.1, and this is where it was installed to. To make a lot of these operations, as Todd talked about earlier, faster, we're going to add a binary cache to our virtual machines here so that we can install more of these pre-built packages just to make this faster for ourselves. And so to go and enable that build cache, we're going to do Spack mirror add. We're going to name this mirror tutorial, but you could name it anything that you wanted to. They don't need to be named something specific here. And then we're going to install it, or we're going to look for that build cache in the /mir directory. Typically, you would be associating mirrors with something like an S3 bucket, or as we'll talk about later, an OCI build cache, which is similar to how you would pull Docker containers or Podman containers if you've used those before. In these virtual machines, we've pre-populated /mir with one of those full environments, and you can make a build cache just any arbitrary location on a file system too. So we'll go ahead and add that. Now we're going to import the GPG keys. We use GPG keys to sign the packages so that you know that you're not being in the middle, and you know that you crossed whoever created this build cache for you. They're going to go sign all of those packages saying that they are the ones who created them. Sorry, please. And then you know that no one else has pushed packages into that repository and not signed them. And you know, even if they get access to the file system, they're not fucking with your installation because we're checking for them securely with GPG. Now that we have added the build cache, let's go ahead and start doing a couple of different builds. And we're going to talk about the Spack syntax here a little bit. So let's again run a Spack install. We're going to install zlibng, which is, if you've ever used zlib, the package, it's just a faster rewrite inside of C. And the first symbol we're going to talk about here is the % symbol. So if we were to say %clang, this is telling Spack, hey, I want to look for in a build cache, or I want to build a zlibng that is built on top of the Clang compiler rather than something like GCC or your Intel 1 API compilers. So inside of our Spack syntax, which we're going to build up here in a little bit, this % symbol is your reference to building a package on top of a compiler. So we'll go ahead and install our version of zlibng here that was built on top of Clang or built with the Clang compiler. We'll give that a second to go find it from our build cache and install it. There we go. It's installed, and I guess it's found and installed a version of zlibng. And so we talked about the power of being able to install multiple versions of packages before. The multiple versions of packages or multiple variants of packages could be packages built with different compilers, but they could also be packages at different versions. So you're not limited to having one version of zlibng on your system. You can have arbitrarily many zlibngs on your system. So here we first, previously we installed zlibng 2.1.6 as shown up here. If you want to look for all of the versions of zlibng inside of Spack, you can do Spack versions and then zlibng. And this will show us, okay, so 2.1.6, that is indeed the latest version of zlibng that we have. But we also have 2.1.5, 2.1.4, etc. So let's go ahead and install one of the later or older versions of zlibng. So again, we'll do a Spack install. We're going to do zlibng. And this time, we're going to use the @ symbol So again, percent symbol is a compiler. At symbol is the name of a version that you want, or a name of a version range, as we'll get to here in a little bit. But we're going to do 2.0.7. And now this is going to go look for a version of zlib at 2.0.7 that is out there in the build cache, or compile it up from source. Okay, so it found one in the build cache, we installed it, and as you can see here, we'll talk about these caches a little bit later, but we were able to install this additional version of this additional version of zlib as 2.0.7 right alongside of 2.1.4, that we had previously, 2.1.6. So because we hash the packages, but also because they're installed into their separate prefixes and Spack is able to connect all of the dependencies up, you can have these arbitrarily many packages. So let's combine both of the two sigils that we've just learned, or actually we'll do that here in a second. First, let's install another version of GCC, or excuse me, another version of zlib, this time built on top of GCC instead of Clang. So we'll again do a Spack install. We'll do zlibng, which is the name of the package. And this time we'll do the percent, specifying the compiler that we want. And now we're going to combine that with a version of the compiler that we want. So you can have multiple versions of the compilers, and this is going to specify specifically that we want GCC 10 or GCC 10 dot something. And we want to build a zlibng on top of that version of GCC. Sweet, so it was able to go out. You can see this time it went and installed another version of GCC runtime. So this is because we asked for a compiler that we had never used before. We're grabbing that package. gmake is a dependency of zlib, so we're building all the way up that dependency tree. And then finally here we install zlib 2.1.6, so that latest version. But this time we built it on top of, here we can see GCC 10.5.0. So you can also add, in addition to these two sigils that we talked about, the at symbol, the percent symbol, you can also pass different C flags, which get passed to your builds when you're doing from source builds. We also match them for binary caches. So if you have multiple versions of a package like zlibng in a build cache, as we'll see here in just a second, passing in C flags will tell us to go find a different version of that package. So again, let's do another install of zlib in G, just to really hammer down this point that we can install many of them. We're going to do zlibng. This time we're going to ask for that older version, 2.0.7 again. But this time we want a version that was compiled with the C flags of dash capital O instead of a 0 here, 3. Dash. This will go out and look for a version that was now compiled without optimization. As you can see, we went out, we found one. This one was built on top of GCC 11.4.0, but it satisfied our request. Now that we've installed all these versions of zlibng, let's go look at them on our system. So whereas we had Spack list earlier, Spack list looks for all available packages. So it's kind of equivalent to searching for a package, looking in the entire repository of available packages. We have Spack find, which shows you just what's installed on your system. So if we run Spack find with no arguments here, it's going to pull up all of the packages that we've installed, separated by the different versions of compilers that we used to install them. So you can see here's that zlibng, the latest version of zlibng that we installed using the Clang compiler. We also have our older version of GCC and the version of zlib that we built on top of that. And we have the latest version of GCC that we have on this virtual machine, and the multiple zlibs that we have compiled for that, or installed from the binary cache in our case. So you can see in total here, we have 4 different versions of zlib across 3 different compilers. Or 2 different distinct compilers, 3 different compilers, and versions of compilers. So here, let's look at the long form of the output. So this is the short form. If we do Spack find -L and F, this will show you all of the differences that make up those packages. So as in the short form, you can see how the versions are different. Here we can see that the versions are different, but also that we get to see, the C flags that we just talked about it earlier, right? So these two look like the same package here up top on the short version, but you can see here that they are actually different. They also have different package hashes, which is a good way to tell that a package has been built in a slightly different way. This hash is generated for every we call them specs, everything that you or everything that you install. These hashes have all the provenance of your build. So the version that it was built with, the compiler that it was built with, the internal build, script that ran to build that package up from source, basically a bunch of the metadata about both your system and the package gets translated into those hashes. So that for reproducibility's sake, if you wanted to redo an experiment later on, you can verify that you built them up, you got the same hash of your package, you're rerunning that experiment, you have essentially the same software environment as you had before. So let's switch gears here a little bit, and let's do a Spack install of TCL to talk about how you get packages into your path and how you end up using them. So we'll do a Spack install TCL here. And we'll talk about one more sigil as we build this up. That's going to be the upper caret here. And upper caret allows you to request specific dependencies of a package. So you can see here we built up this version of TCL. We built up and used a version of zlibng 2.1.6. But say that we wanted to build a TCL with a version of zlib that is 2.0.7, for example. And maybe you even want a very specific version of the compiler used. So we can build on this language that we're building up for folks. We're going to do Spack install TCL again. We're going to say up caret, and then we're going to say zlibng. And so whereas before we were saying, hey, I want to install zlibng, this up caret is instead meaning, hey, I want to install TCL, and I want this TCL to be built on top of zlibng. So zlibng here is a dependency, not what we would call a root Spack in your installation request. And then for both of those packages, realistically, this is saying that you want a zlibng 2.0.7 built with Clang, but we'll often optimize so that if you apt for a specific package built with a compiler, we'll unify as much as possible and use that compiler for other packages as well. So this is going to go out. It's going to look for a version of TCL built with this version of zlib, built on top of Clang. You can see it finds it pretty quickly from our binary cache and goes ahead and installs it. And now, if we wanted to, we can look at that long form again to see all of the differences in these TCLs that we've built. So you can see that we have one TCL down here built with GCC 11, and the other one is up here built with Clang. So we touched a little bit onto the, all of these hashes here, right? A little bit. And someone said in the chat, I just saw it pop up a little bit, how can you see the long form of the hashes? If you did a Spack find -H, this gives you only the hashes of the packages, but might be useful for some piece. But you can do format strings instead of Spack find. And so you're able to output that long form information along with the name of the package or the version if you want to do it that way. We can also, say for reproducibility's sake, if you really want to get exactly the same package again or pull out a very specific version of a package from a binary cache, we can do a Spack install. And this time we're going to say, hey, I want to Spack install TCL, and I want to build it on top of a zlibng. So let me really quickly go and show this for everyone. So we'll do our Spack install again. We're going to do TCL. But this time, I want to build it on top of a zlibng that starts with 6bh. So if we go ahead and look into our zlib-ngs, that's this one right here. So I can say, I want to build a TCL on this exact zlib-ng, the one that's got the C flag for the optimization criteria. So here we're going to do /6ch. We don't have to give it the full hash. We just have to give it enough to be unique. But the slash sigil here is saying, this isn't the name of the package. This is the hash of a package. So we'll go ahead and do this install, and we'll see that we are able to find and then install a version of TCL from the binary cache that was built on top of this specific version of zlib-ng. Mm-hmm. If you want to be able to see these dependency orderings inside of Spack find, we'll do Spack find -d. And this will show us all of the packages that we've installed with those different compilers, but it will also show us, this is the TCL that we just installed, and these are its dependencies. So we can see, the versions of zlib that it just installed, or the version of zlib-ng that we used to build up this package. So this gives you a pretty good set of criteria for like, hey, how are my packages installed, or what are the dependencies of the packages here? We'll talk here in a minute a little bit about a nicer way to visualize that, but this is helpful for checking out and looking at a brief glance what packages has been installed with what. So far, we've been talking about pretty easy packages to install, right? Like TCL, zlib-ng, these things have very few dependencies. And if life was that, we probably wouldn't need Spack. It would be pretty easy to do a couple of make installs, but Spack can also install much more complicated packages. So here, let's do a install of HDF5. We're just going to do a plain, no sigils, no specific @ symbols and such. It's always tempting the demo gods when people ring your phone. So this is going to go ahead and it's going to, what we call concretize, basically take your abstract, hey, I want to install HDF5, and it's going to come back and it's going to say, let me find you the specific version of HDF5 that fits with all of the dependencies, and let me figure out all of the dependencies, all of their exact versions that we need to go install. So that's how we take what we call a abstract spec and turn it into a concrete spec inside of Spack. I think Todd's going to give you guys a little bit of a rundown on how all of that works. But basically, you get this concrete dependency graph with all of the exact versions of how to install a package. So as you can see, HDF5 here is much more complicated than something like TCL or zlib-ng. If you look here at the top, you can see that we have 43 packages that were installed here. Cool. So we installed HDF5, 1.14.3, which is likely the latest that exists in the build cache here, and all of its dependencies all the way up, including OpenMP here. So now let's talk about another of the sigils that we have inside Spack. That would be the plus and the tilde, which enable or disable variants respectively. So Spack install HDF5. If we do tilde MPI, this is going to disable MPI. If we did plus MPI, which is the default for HDF5, but if we wanted to explicitly make that no, we would do plus MPI. So this is kind of optional functionality that exists in a package, right? You've got your base package, you've got plugins or extensions or additional functionality, which makes that package larger to install. So in the case of the sigil and MPI here, we might say, hey, I want an HDF5, but I want it to be as small as possible because I'm putting this on a small home allocation or something. So we'll go ahead and do that build, and it's going to look for a version of HDF5 that does not have the MPI capability or was not compiled with the MPI flags and capability. And we should see here that we're actually going to reuse a lot of our previously installed packages. And so over here on the guide, you can see this is what the plus symbol means here. It says, hey, I found all of your dependencies already Yep. So right here, I found all of your dependencies already in your install tree. Like you've already installed them previously. So I'm going to go ahead and just pull the latest version of HDF5 and then install that. And so you can see that the last message is now, here's all your dependencies, they're installed, and now your top level HDF5 is installed as well. So Spack allows you to, build on top of this language for even more complex expressions so that we could write something like Spack install HDF5, whereas before we did tilde-npi to disable it. This time we're going to say, I want HL support and I want NPI support in my HDF5. But we can also use that up caret, which we just talked about a little bit earlier, to be able to say, instead of using OpenMPI, which I pointed out a little bit earlier, let's build it this time on top of impitch, which is a different MPI provider. So here we'll use that up tilde, and we'll say, I want to compile, or I want my HDF5 to depend on impitch instead of something like OpenMPI. We go ahead and run this installation. You'll see, again, we're reusing most of our dependencies here, but then we're going to build up everything that we need to install impitch and then to build a HDF5 or install an HDF on top of impitch. So we go ahead and we install a version of Python, a bunch of the dependencies for impitch here, impitch itself, and then that last HDF5. So now if we go back to what we had before and look at, this time we're going to do Spack find, we're going to do -L for long, -D for the dependencies. We can see that we get some much more complicated dependency trees out of here. So if we want to go and look at that, so here we have like OpenMPI, which we installed when we installed the first version of HDF5. You can see much more complex dependency trees with all the dependencies all the way down. And then we can see here impitch and its dependencies that we went and installed. So a good way to kind of look at a dependency tree quickly to see what versions of dependencies your packages have been built with. But the prettier way of doing this, at least in my opinion, is typically to use the Spack graph command instead. So here we'll write Spack graph instead of Spack find, Spack graph, and let's do a graph for that package that we just installed. So we'll do HDF5 here with those same dependencies. So plus HL plus MPI. And then we'll go ahead and, again, we want all of this to be using impitch as a dependency. And so if we run this, Spack is going to generate us a nice ASCII graph. And it's going to nicely show us all of the dependency relationships between our different packages. So I'll show a preview of here on the right that's in the documentation. We'll give Spack a minute to create that nice pretty graph and look at all of the dependencies that it has to here. So there we go. It's always nice when you get to see the terminal output compared to the docs because we actually have colors over here. So each of these colors is representing a unique dependency. We do run out of colors at some point, and so you're reusing yellow a couple of times in this tree. But you can see here's our top level HDF5. And then you've got your impitch and your dependencies all the way down. And so we can see that like tar depends on a couple of different things inside of this graph down here, down below. And all the way at the very bottom of this, we've got our GCC runtime modeling or compiler, and we've got our version of gmake that everything depends on all the way down here. Okay, so if you thought that was the complex dependency tree, let's go for something even more wild. famously in the research, I guess, ecosystem, there's a package called Trilinos. We pick on it a bunch, but Trilinos is a really big dependency tree. So let's go ahead and let's Spack install Trilinos. I can type. And you can kind of get an example, looking through the docs here, you can see how many packages end up getting reused, but then there's also a lot of packages that we're going to build on top of to install Trilinos here. And this is really where, Spack begins to shine. You have these, if you were to think about packages in the research ecosystem, they're not atoms. They're not built in isolation. They're really like complex molecules. And the interesting science happens when you look at long, complex molecules. Something, if you were trying to model DNA, you have lots of connections there. In the package ecosystem, we have very complex pieces of software that build on top of all of these smaller libraries so that we can do really cool science. And Spack helps to tame kind of the wildness of those ecosystems by letting the computer figure out the dependencies for you and allow you to give this language to specify your build rather than having to tweak all of your builds by hand at every stage all the way up. And you can see, an example of Trilinos being kind of just a crazy build. Trilinos, if you were to do it from source, takes about 3 hours to build all the way up. But those 3 hours aren't you in the middle having to sit there with different make files and iteratively go through the process. You run Spack install Trilinos, it takes, less than 20 seconds of your time, and you let the computer go off in the background or overnight in a HPC allocation, go off and do the build for you. So what we'll see this, pop up here in a minute is the Trilinos install, if it goes out and finds a version of Trilinos that we can install from the binary cache. And then we'll add a couple of variants on top of it here so that we can say that we build it with impitch instead of OpenMPI, build it with the HDF5 functionality. So this is just kind of giving some examples to what we talked about earlier. Plus HDF5 is enabling the variant for HDF5. And then we say, okay, so because we're building the HDF5 capability in Trilinos, it depends on HDF5. I want to modify my dependency of HDF5 so that I know that it builds with HL support and with MPI support. And I want to know that this HDF5 is built with impitch. So you can see this gets to be a rather complex build, but we're able to talk about it in relatively simple terms on the command line. I think, again, this is, you get lots of people onto the same VM, and we're doing lots of installs here. So we might skip this variant and drop down here depending on how much time we have left. I guess I see questions flying in the chat, and hopefully...
We got them.
Okay, cool. So I guess, while we're waiting for this to finish concretizing, feel free to ask questions inside of the chat. I think Todd and Greg are answering them for folks. We'll also talk about, like if you want to see just the dependency madness that is Trilinos here, we'll jump back to Spack find D after we're installing it here. And you can see just how many different packages get installed. So you're building on top of CMake. You've got your GCC runtime, your libc, which we're now modeling inside of these graphs for Linux systems. Cocos, which is a portability layer that comes out of Sandia National Lab. And all of those dependencies all the way down. hoping that my access to the VM here wasn't like suddenly terminated. Is it hanging? So I might just see if we can SSH in again into that, just to double check that it's not a network problem.
I think we have more people than usual on these VMs today.
That's probably true. Looks like I can't even get into the VM, which might be lots of people doing compiles or working on stuff.
You have actually 10 people on that particular node.
Yeah, we didn't particularly load balance that.
Yeah, I think we should have done more VMs for today because it's a bit loaded on the horizontal.
So that's all right. Well, we'll give this a couple more seconds to see. I would totally do top if I could log in, because then we could see. But it seems like it is so bogged down that it's not timing out. So it doesn't seem to be a firewall issue, but it's definitely crawling as a poor little VM. We like to abuse our AWS VMs for folks in tutorials, I guess, is what we've learned today. Anyone from AWS is here, we're sorry, and we appreciate access to the VMs. So I guess we'll keep moving forward here and then see when the VM comes back, because we do have other parts to get to. So, similarly to up here where we're looking at all of these dependencies in Spack find, we can again look at the pretty graph version of Trilinos here. And so you can see that you've got Trilinos as what we call the root spec, or the top level package that you're installing here. And then its dependencies all the way down. So OpenMPI, all the way down. You can see all these different versions of the packages. And then the dependency relationships here, you can see they kind of fan out so that many of these packages depend on many of other ones. If you've got something as complex as Trilinos that you want to install, or that you want to look at the dependency graph of, ASCII might be kind of hard to follow, right? Like if we're looking at an ASCII graph like this is pretty complex and a little hard to look at. Spack graph also supports outputting to dot formats. So when Todd earlier in the presentation showed folks that big dependency graph of Aries, that's a dot graph. We can export in the dot ecosystem, and then you can compile that into something like a PDF or a PNG with GraphViz. So if you've got a really complex dependency tree that you want to look at, or that you want to throw in a presentation, we're always happy when people make presentations built on top of Spack in one way or another. If you want to give a presentation about a really large dependency graph, look at Spack graph --dot, the name of the package that you're installing, and then you can pipe that output to GraphViz or dot, the tool in this case, and render out a PDF. And this poor node is very bogged down.
Let me get you a new node, Alec. You can keep going as best you can. I'm going to make some more VMs with bigger instances.
That would be perfect. Thank you, Todd. Sure. Okay, so building on top of our knowledge for, we've talked about install, we've talked about find, we've talked about graph. It would seem pretty logical that, let's talk about uninstalling packages now. So if we were to go run Spack find and look at the, I guess you've got your the package that you've installed and then your dependencies here. We go look at that. We might want to, at some point uninstall a package so that you're not growing exponentially. So here we can use the Spack uninstall command. So simply Spack install installs a package, Spack uninstall removes a package. So if we were to run Spack uninstall zlibng at a specific version of GCC, this is going to remove that version of zlibng that was built with GCC 10. And here we're using -y just to say, if you were to do this without -y, it's going to interactively prompt you and say like, hey, do you really need to be uninstalling this package? But yes, for this tutorial's sake, we really know what we are doing. We are not having a late night rm-rf session. And so if you do -y, name of the package, it's going to go ahead and uninstall that package. So you can see this is all the build provenance for that package. It'll go and uninstall zlibng there. And if we were to run spack find again after that, you're going to see up here, whereas we had the 3 different compilers, because we uninstalled the one with 10.5.0 or GCC 10, we now only have 2 compilers listed here. So we got rid of this zlibng built on GCC 10, and Spack got rid of that whole row of packages for us. If you are to run spack install or spack uninstall and a low-level dependency, something like zlibng that lots of packages are built on top of, Spack is going to refuse to uninstall it. It's going to say, hey, I don't know if you know, but if you do this, you're going to break a whole bunch of upstream installations. And so if we were to run spack uninstall zlib, and again, the slash is referencing a specific hash here, we go and uninstall that, then we will, or if we try to uninstall that, Spack's going to refuse. It's going to say, hey, look, you still have this version of TCL that builds on top of this version of zlibg. What you probably meant to do there was also want to uninstall TCL. And so there you'll do spack uninstall --dependence. And if you ran spack uninstall zlibng, this version of the hash, or spack uninstall dependence, and this name of the package and hash, that's going to uninstall both zlibng and this version of TCL. If you just wanted to say, I want to force it, so I really do want to break my upstream installations, you also have that option. But most of the time, you're going to want to run spack uninstall dependence. Dependence is long form for -R. So we'll here run uninstall -y, again saying, yes, I know what I'm doing. -R, I want to delete all of my upstream dependents for zlibng. And so now we should talk about, we installed, or hypothetically, if the VM didn't die, we would have installed multiple versions of Trilinos. And so here, if we say spack uninstall Trilinos, Spack is going to come back and it's going to say, what version of Trilinos do you mean? There are multiple versions of Trilinos installed. You didn't tell me which one to uninstall. You weren't specific enough. And so here we can see it lists both of them for us. We've got one that prefixes with the hash JLX and one that prefixes with the hash UGM. So to be more specific, we'll reference the JLX hash here and say, spack uninstall this specific version of Trilinos. And as you see, it gives you the little interactive prompt because we didn't say -y here. We'll say yes, and then it will uninstall the version of Trilinos that we asked for. Okay, so jumping back into a VM, if you just grabbed a new VM that's one of the bigger ones, again, we're going to need to clone Spack. And I'm going to fix my prompt here, make it a little bit smaller for folks. So again, we'll do a git clone. We're going to do a dep equals 100, and we'll do the branch that we want is going to be releases v022. And then this is going to be https://github.com/spack git. If folks are jumping into new VMs, that's where we're going to clone Spack from. And then once you do that, you're going to want to cd into the Spack directory, and then we're going to want to source the inside of share Spack setup env.sh so that we put Spack back into our path. So now that you can see if we run Spack again, be able to see that we can use it. So inside of Spack, we talked a little bit about using different compilers to build up different variants of packages. And a lot of people ask, like, hey, can I install a compiler through Spack and then use that as one of my compilers? And the answer is yes. This is going to change a little bit in the next release. We're pushing towards compilers as dependencies inside of Spack. So in the future, if a package depends on a specific version of a compiler, we'll just automatically install that for you. But as of right now, if you're using v22 or v0.22, you have to still do this. So we'll look just by running Spack compilers to see what compilers are currently available. Because this is a new VM and we haven't run any Spack commands yet, there are no compilers. But if you run Spack compiler find, that's going to look for all the compilers on your system. And after this completes, we should see that we've got a version of Clang and then 2 versions of GCC available. That newer version of GCC and GCC 10, which we used for our TCL builds earlier. Perfect. So now if we run Spack compilers, you'll see that we've got those 3 compilers set up. And here, let's say that we want to add an even newer version of GCC. So we'll do Spack install GCC. We're going to do GCC 12 in this case. So again, we'll use that @ sigil at GCC 12. And this is going to go out from, I did not add the mirror. So again, we should probably do Spack mirror add. We're going to add the tutorial mirror, and it's coming from /mirror. Add. And then we're going to want to do Spack build cache keys import or install -- install. Okay. There we go. So we've installed the keys from our build cache, and now let's go and install GCC 12 from that build cache. So Spack install GCC using the @ sigil and 12. Sorry, and that was a bit fast for folks who are running up against the break here, but if you logged into a new virtual machine, make sure to go back to the top of this page to adding the build cache so that your builds are fast and it's not trying to pull from some other location. So we'll go ahead, we'll find a version of GCC. It's going to be a little slow here on the first just because it's got a bootstrap itself. And there we go. We're going and installing our dependencies, building all the way up to that GCC tool chain. And you can see we're now installing GCC 12.3.0. And once this finishes, we can go look for that version of GCC just by using Spack find like we've done previously. If you do Spack find -p, this is going to output the prefix of your package. So it's going to output that location where we installed GCC to. And we can use that to direct Spack compiler add at that location. So this is the location where we installed GCC 12, and then we're going to do a Spack compiler add. So we're importing that Spack built GCC into our system as a new compiler for us to be able to use. It's GCC is rather large, so it took a second to grab the file and then unpack it and untar it. So, and then this is just about the end of the basics and getting started with Spack. So we've talked about looking for packages using Spack list. We've talked about installing packages with Spack install. We've talked about looking at your installed packages on your system with Spack find. We've talked about many of the ways that you can customize builds. And here I'll go ahead and add that compiler. So if we do Spack compiler add, and then we're going to do Spack location, gives you the different locations that you might be interested in for a package. So Spack and location -I is going to find you the installation prefix where you installed GCC 12 to. So we'll go ahead and Spack location -I GCC 12, and we will add that. So now you can see we've added a new compiler, which is that GCC 12. So if we go back and run Spack compilers, we can see we now have the 3 versions of GCC here. So now we could do builds on top of any of these 3. Spack doesn't care that one of them was bootstrapped with Spack. And, you know, if you've done a scaling study or you tweaked a bunch of your builds and you realize, you know, I don't really need this compiler anymore, you can run Spack compiler remove to delete a compiler from your configuration, not from your system, if you were installing in Spack. So Spack compiler remove GCC at 12. And again, if we run Spack compilers, we'll see that we're back down to just those 3. Now, this didn't remove GCC from our system, but it removed it from the available options that Spack had to choose from when it did a package install. So you still have GCC 12 installed on your system. If you wanted, you could Spack uninstall GCC 12. I'm not going to in this case, but you could do that. That would actually remove the package, but this removes it from the configuration. Yeah, so that's installing, uninstalling packages, looking for them in the systems, being able to install specific versions of packages using the @sigil, installing them based off of different compilers, so Clang different versions of GCC with that %sigil, and then using the up caret, you know, so that we talked about build-ng up caret and a dependency like a different version of gmake. We'll build that version of the top level package. This is the top level package built off of this dependency. So you can use that to specify different versions of MPI or different versions of packages. And with that, you should have a pretty good grasp on the initial use of Spack. So we're going to dive into more of the complex use cases, configuration environments later on today, build caches tomorrow, developer workflows, and scripting. But with that, I'll hand this back over to Todd.
You have seen a lot of the basic usage of Spack thanks to Alec. And we're going to try to tie some of the ideas from that together here in this section by just covering the core concepts in Spack. All right. So, core concepts. Most tools do not support combinatorial versioning like you saw. Alec installed a bunch of different versions of zlib and other packages, and your traditional binary package managers like RPM, Yum, apt, and so on are really designed to manage a single stack that upgrades in place. And so you get one version of each package at a time. If you upgrade it, it upgrades in place. And the idea there is that you're managing upgrades to a stable and well-tested system stack. Port systems tend to do the same thing. It's got the same sort of single prefix layout, at least in portage and Mac ports. There's not a lot of support for parameterization in most of the systems. Homebrew does install things to separate prefixes, but it doesn't parameterize them nearly as much as Spack does. In fact, they try pretty aggressively to remove options from the packages because they want to make sure that they have sort of a canonical binary for everything. And then you can get different versions of things by using a container or a virtual machine. But what you're doing there is duplicating the whole OS stack. So instead of installing 2 versions of an application, you might be making 2 different versions of your whole system, each of which has a different version of the application. And so we're trying to handle the combinatorialness down at the package level. So you saw that Spack provides a syntax that lets you describe custom package configurations. So Alec went through a number of these, but you've got Spack install MPI leaks, Spack install MPI leaks at 3.3 to install version 3.3. You can specify the compiler with a %sign. You can specify variants, so options on the build. Each package can expose its own variants. You can inject flags into a build. You can set the specific build target that you want to use to optimize for a particular microarchitecture. And you can refer recursively to packages in the dependency graph there. So if you want to set the version of mpitch that you're using with your MPI leaks build, then you can put the @ sigil on the mpitch spec there, and and customize the mpitch installation. So this lets us talk about different package configurations, and we call each of these things an abstract spec because there may be many different builds of MPI leaks, or even many different builds of MPI leaks at 3.3. Each one of these describes sort of a slice out of the space of possible builds. And so that's what you're asking Spack to get you. Get me the best one of these. Right. So in addition to the spec syntax, the second thing that you probably ought to know if you're thinking about core Spack is that there are these package recipes. And we'll get to this tomorrow, but in the main line, there's about 8,000 of these, and they're for all the packages that people have contributed to Spack. These are package.py files. They essentially define two things. So up here at the top, there are a bunch of directives that tell you the space of possible builds for a project. What are all the options? What can they be set to? Down here at the bottom, there are instance methods that essentially define how, given one configuration selected from that space, you could get it installed into a particular prefix. So it's really like this is the space up here. These are the things you could build. And this stuff down here is the recipe for building one of them. So what you've got here is there's a Python class. It's got a docstring that just gives a little bit of commentary on it. Like this is used for the help when you say Spack info, that package. There's a home page. There's a URL that tells you where to download a tarball. And Spack is smart enough to infer from this URL the URLs for other versions, assuming that they're regular. Sometimes you have to specify them as sort of one-offs in the package. But here, it just knows that if I want to download, version 1.1, it can find the version in that string and say, oh, I'll swap it out for 1.2.3 and give you a different one. So there's 3 versions defined here. Each one has a checksum, and the checksum basically says, that's how we check whether we got what we expected, and that someone's not trying to play a trick on you or give you a malicious binary or malicious source tarball when you download a package. There's 2 options for this package, so you can build either with or without MPI or with or without OpenMP. So it's these variants here. They both default to true, so they're on by default, and you can turn them off on the command line using some of the syntax that Alex showed earlier. And then finally, there's optional dependencies. So it depends on MPI when MPI is enabled, when plus MPI. That basically says if you disable MPI on this package, we're not going to have an MPI dependency. If you enable it, then we are. And this down here says the package depends on CMake, but it needs at least version 3.0. So the version specifier here is kind of like a Python array slice. And it's a build dependency. So it's only needed at build time. It's not needed after the package is installed. Then down here, there are these instance methods. Essentially what's going on here is you're translating. So the install method is really all you need for a Spack package. It just happens to be a CMake package, so it has a little extra support for invoking CMake with arguments. The CMake framework will run this CMake args method. It'll run CMake for you, and then once it's done with the build, it'll run install. The CMake args method is basically just saying, I'm going to translate the configuration I'm given, so that's self.spec, to CMake arguments. And so if OpenMP is enabled in the spec, then we put enable OpenMP on the equals true on the CMake line. If OpenMP is disabled, this becomes enable OpenMP equals false, and so on. We'll get more into the details of packages later in the tutorial. So tomorrow morning is the package creation tutorial, but you get the idea. There's a space of things you can build, and then there's a recipe to build one. And that's how you write a package file. We can do an awful lot of conditional logic in Spack packages. And this is one of the reasons that we've spent a lot of time working on Spack's dependency solver, is so that we can support things like GPUs and ecosystems with lots of conditionality. So you can see here, this is CUDA package. This is not the package for installing CUDA itself, but this is something that you would extend if you're building a package that uses CUDA in Spack. And so it's just an example of how we can encapsulate a lot of logic into a superclass for common things that people would want to do in their build. And so in this case, it's basically if I want to use a GPU, then I have a variant CUDA that can be enabled or disabled. If I enable CUDA, I also have a variant called CUDA Arch, and that can basically be a number that indicates what compute capability the GPU has. There's a conditional dependency on CUDA itself when CUDA is enabled. And then there's a whole lot of logic done here that defines essentially what versions of CUDA support what CUDA architectures, so that you can just ask for a CUDA architecture and Spack will impose a constraint on CUDA that says, like, okay, if you want 75, then you need CUDA 10 or higher. And then down here, there's even more constraints that define how CUDA gets along with different compilers. And I think a lot of people know that CUDA is sensitive to what language version your compiler supports. So there are constraints imposed on the compilers that you're using, depending on what version of CUDA you're trying to use. So you can see that with this spec syntax, which we use a lot in the package DSL here, we can express an awful lot about packages, and we can encapsulate things in a superclass that anybody can leverage, which is why we're able to have a lot of different CUDA packages in the Spack ecosystem. Spack specs so one of the things you may have noticed when Alec presented this is that there's this caret, that depends on operator or sigil that you can put on the command line. And one of our goals with Spack was to make it so that you don't have to think about the structure of the dependency graph underneath the thing that you want to install. But if you do want to talk about a node that's in there, you can just refer to it by name. And so here, what you're doing is you're saying, okay, MPI leaks with the Intel compiler, I want to install that. But I know that, say, the latest version of libelf is breaking my build. So I want to build an older version, or I want to reproduce an older build. And I want to say, use libelf at 0.8012. I don't have to know that that libelf is a dependency only through this chain here, from MPI leaks to call path to dynast to libdwarf to libelf. So I don't need to know that. I just need to know that something about this is breaking and I want to change it. So I'm going to say depends on libelf at 0.812. Spack will gripe at you if you specify something that's not in the dependency graph. So you're guaranteed that whatever constraint you apply here is going to apply to your graph. You may have noticed that it depends on MPI when you see it in a package description, like the one for cryptkey earlier. MPI is not actually a package. It's an interface, and it's a standard that lots of different packages implement. So there's OpenMPI, there's mbappage, there's mpitch, and so on. And we don't want to have to write 10 packages for 10 different MPI implementations. And so the way that we handle this in Spack is with what we call virtual dependencies. So essentially, when you have a package like MPI leaks or call path that need MPI and that need to make calls from some MPI implementation, you depend on the interface, not the implementation. And then the user can go and specify a particular implementation if they want to. So you can say Spack install MPI leaks, depends on mbappage at 1.9. If the package depends on MPI, this is fine. We'll swap in mbappage for the MPI implementation. Same for OpenMPI and so on. You can also specify the version of the MPI interface itself. And different versions of mbappage support different levels of MPI. Different versions of OpenMPI support different levels of MPI. If you ask for, say, MPI at 2, it means give me an MPI implementation that supports MPI 2. So all the new features that came along with MPI 2, or maybe 3. This is more common in the package itself. So like you would have a package that depends on MPI 3 or higher if it needed to use those features, so that it would be sure to get an MPI implementation with the features it needed. And you can write it on the command line as well. It'll just constrain which implementations that Spack can choose for you. And as you may have guessed, to put all this together, to take the user request from the spec syntax and the information provided by packagers in their package recipes, we have to solve the problem of basically satisfying all those constraints. And so when you ask Spack to install, say, MPI leaks, depends on call path 1.0 plus debug, depends on the libelf at 0.8.11, we call this an abstract spec. And we call it that because it's not a full build configuration, right? It's giving you a few things that the user cares about that need to be set in the build. But then Spack has to go and fill in the blanks for the rest to make some sort of consistent installation description. And so what it does is it takes that and it makes a graph out of it. It fills in all the blanks for all the things that are not specified in the graph. So for every node, it fills in a version, it fills in a compiler, it gives values to all the variants. And some of them may be determined based on constraints that are in the package or conflicts. And then finally, once we fill in all the blanks, we store that detailed metadata in a JSON file in our database, and you can go and query it later. So you'll see, and you saw with Alec when he ran Spack find, that you can say, hey, show me all the packages that were built with GCC 473, or show me all the packages that depend on this version of zlib. And you can filter based on this information that we store. And so it's really the concretizer that takes this abstract spec and converts it into a concrete build description that describes exactly one thing that you can build. And the concretizer is it's a solver that we'll get into the details of in a minute. To handle all those configurations, so I mean, you can imagine with a specification like that you could end up with lots and lots of different versions of zlib, as Alex showed. What we are doing when we install things in Spack is we're guaranteeing you that every one of them gets its own installation directory. So everything gets a unique prefix for its configuration. And to do that, we take the dependency graph, we take the concrete version of it, so with everything filled in, and we make a hash out of it. And so essentially every node in this graph gets a hash, and it gets an installation directory that corresponds to the nodes in the graph. And so you can see that here. And that's how we guarantee that everything gets that everything has its own install prefix, and that you could install 500 versions of MPI leaks if you wanted to. The other thing that we do to ensure that things work the way you built them is we don't use things like LD library paths that require the user to set something in their environment in order to make libraries work for packages. If you've used LD library path, it's a global environment variable you set for yourself. You may be working with 3 different pieces of software, each of which uses a different version of some dependency. And so LD library path can cause all kinds of havoc when you use it that way. So instead, what we do is we embed rpaths in the binaries. And rpath it's part of the ELF standard, or it's the field in ELF that's used by the loader. And essentially what it does is it's like LD library path, but it says for this library, go and find its dependencies in these locations. And so we're essentially baking in the knowledge of where to find dependencies into every library in Spack. And that ensures that, by the time you get around to running something, you may not be the person who built it. You may not remember how you built it, but we do, because we've baked in the paths to the libraries into all these things. And so each of these directories, even though it has a separate install directory, it points out to its dependencies so that we can find them later. And you can just run a Spack binary out of a directory. We use compiler wrappers to ensure that those rpaths get added, and also to do things like inject flags, like you saw in the basic uses tutorial. I'm not going to get into all the details of how this works, but essentially this is how we swap compilers into builds. So when you say build with this compiler instead of that one, we're really injecting wrappers into every build. And then behind the wrappers, we invoke the real compiler with some extra arguments added. So we add includes and library search paths, and we add rpaths so that the binaries that we build can find their dependencies, and so the compilers can find the dependencies as they're being built. Spack has support for external software, and you'll see more about this in the config section later in this session. And essentially, you don't have to build with an MPI that was even built by Spack. You don't have to build with, you don't have to use Spack's version of any particular package. You can tell Spack that there's an external installation of something, say OpenMPI, in some path. And essentially what you're doing is you're giving it all the information you can about it. You know the version, you might know what it's built with, and so on. You might know some of the variants. And you tell Spack, hey, that thing lives here. And then Spack can go and leverage that package in a build. The one disadvantage of this is that we won't have information about the transitive dependencies of the thing that you register as an external. So if you register OpenMPI as an external, we don't know about all the stuff below it to ensure, maybe that another version of HWLock depended on something that Spack built is compatible with the one that OpenMPI uses. So if you use externals, some of these compatibility issues are on you. And so the graph will look like this, because Spack doesn't really have knowledge of how that thing was built. We just know that you told us about it in your configuration. So we'll get more into that later. Spack has support for private package repositories. So those package.py files, there's 8,000 of them in the built-in repo. When you clone Spack, you get all 8,000. We'll show you how to edit them and look at them later. But if you want to, if you have a code, like say our multi-physics codes at Livermore, like Marble, which is ICF code, if you have one of these and you want to keep certain packages internal, then you can create your own repository, add a package to it, and build your own packages on top of the built-in ones. And so you can see here that there are lots of different layers in Marble, and essentially a lot of teams will build in something that might look something like this, where you've got all the open source packages down at the bottom. People try to push those up to mainline as much as possible because we maintain that over time. There might be a set of packages for your working group or for your division. And then for your team, you might have your own set of packages on top of that in your own repo. So you can layer these things as much as you want. And that enables you to sort of keep some of these things internal and still leverage all the open source packages that are out in Spack mainline, or maybe some other repositories in a more shared internal repo. We have something called mirrors, and you've been using these to fetch source from as we've installed things, and also to fetch binaries. And essentially, Spack looks in a lot of different places for the things that it fetches in order to build things. And so the first place it'll look is in a local cache. Every time you download a tarball with Spack, there's a local cache of all the things you've downloaded. You can clean that out. There's a Spack clean command that has some options for that. It'll look in a mirror that's set up in the shared file system, if you have one. And so if you've set up your local mirror, it might look there. It can look in S3 buckets. It can look in an OCI registry. And then finally, if it can't find anything in all the registered mirrors that you have, it'll go out to the original source for the package on the internet and try to fetch it from there. So there's more documentation on this at spack.readthedocs.io if you want to learn more about how to set up different types of mirrors. Spack does come set up with an S3 bucket, or at least a CloudFront distribution of one, for its default source mirror that has a lot of tarballs in it, so that if certain sites go down, Spack doesn't go down with them. All right. Any questions on that stuff before I move on to a little more details on the concretizer? Yeah. Or I guess ask in the chat and folks will handle that. All right. So the concretizer, we talked about it a bit. It converts abstract specs into concrete specs. It takes that information from a lot of different places. And so there's a ton of constraints there that have to be put together and solved. And essentially, they could come from the package files, they could come from the command line, they could come from configuration files that you set up. We'll get into these later. But they all get dumped into one big solve, and its job is to come up with a concrete, fully constrained dependency graph that you can build. And that problem is NP hard. You have to deal with diamond constraints, and essentially anything in the graph could affect anything else in the graph. So it's an NP hard problem. We are using something called answer set programming to handle the solver internally. So the concretizer is implemented with Klingo, which is an ASP solver. You don't have to know any of the details of this to use Spack, but so that you know what's going on, essentially what we're doing is we're converting all these facts about packages into ASP. It looks like Prolog for anyone who's used that. And we take that and we dump several, tens or hundreds of thousands of facts, plus a small logic program with some rules into this solver, and it spits out a valid and optimal configuration of the dependency graph for us, and we go and reconstruct that. Originally, we used an algorithm implemented in Python, which did not have all the features that we need for all the conditional logic that we have today. And so we, three-ish years ago, we rewrote this whole thing in Klingo, and we've been using that since. One of the things that the new concretizer enabled us to do that the old one did not is reuse installed packages. So if you've installed CMake, say, and then you update your packages, so there's a newer version of CMake available, old Spack would always try to use the latest version of everything. And the way that it would do that is it would take this dependency graph, right, and it would solve it. it would take the concrete spec for the thing, and it would generate hashes for every node. And the way that we would do reuse before was we would say, okay, well, are any of these hashes installed? So for each one of them, we'd say, hey, is this there? And if the exact hash was not in the database, then we would say, oh, well, we have to rebuild that. The problem with this is that small changes to your package can cause the hash to change. And so we would get a lot more rebuilds than people probably wanted. CMake, version of 3.2.1 is probably fine if you have 3.2. If the latest is 3.2.2, you can probably build with the one that you have installed. So we don't want to be as sensitive to all those version changes. So now reuse is the default, and it's a lot more aggressive. And essentially what we're doing internally in Spack is we're telling the concretizer through these facts about all the installed packages. So we say, hey, here's a hash. Here's all the things that you need to know about it so that you can check compatibility. And it's surprisingly simple to tell the concretizer to minimize the builds that it does in answer set programming. So we can say, hey, if you can choose a hash for any package that you want to install, if there's an installed package, you could choose to use the installed version. If you do that, you have to impose all the constraints. So you have to make everything compatible with the version that's already installed. You can't change any of that because it's already built. If we're using that hash, we have to use it exactly as it is on disk. We define a build as something that doesn't have a hash, and then we just say minimize builds after that's done. And so all of this in ASP ends up being very short, and we're able to choose a configuration that uses the most packages that we can from the installed options. And so this is the default now in Spack. And so if you installed before for something having just pulled from Git, gotten all the new package definitions, you might see something like this, where it says, okay, I'll build HDF5 for you, but I didn't find anything I could use. So here you go. I'm going to build all of these different packages to make it work, just because I needed a new CMake. And with reuse, you'll see something more like this, where essentially all of these things are already installed. There's 16 reusable packages that you don't have to rebuild. CMake 3.21.1 was fine. We didn't need 3.21.4 to build HDF5. And the builds go way faster now that we have this kind of logic in Spack. So that's what you're seeing when you do an installation. This is stateful, so it is looking at what you have installed and trying to reuse it. So it depends on what you have installed, what result you're going to get. If you want something deterministic based on the package files that you have, you can still use --fresh to get the old behavior. And essentially, this is like an upgrade. That's why we call it --fresh. It says, give me the fresh definitions of everything. Don't try to reuse the things that I have installed. I don't want any of those. I want the freshest build of this thing that I can have. And so you can say Spack install --fresh if you want that behavior. But reuse is the default, mainly for convenience. If you want to see what Spack is going to do, like you saw earlier, you can use the Spack spec command. And that's the gist of the concretizer. So the final thing that you probably want to understand to really grok Spack is that in addition to the specs, the package files, and the concretizer, we have something called environments. And environments you could think of as a way to document exactly what you want to install. So there's the spack.yaml, it's a manifest. It may include some configuration, or maybe you write some configuration directly in it. And then it has a list of specs that you want to install. So if you want to install these 3 packages, or maybe more, then you make a list of them in a YAML file like this, and then you can say Spack install that environment. And Spack will concretize the whole thing together and spit out a spack.log file. And really, you can think of these two things as analogous to an abstract spec just for multiple packages and a concrete spec, and again, just for multiple packages. And so we're going to cover that more in the environments tutorial right now. All right. So Alec, do you want to go ahead and take, or Greg, are you doing environments, or Alec, are you doing it?
I'm doing environments.
Okay, awesome. So Alec's going to take over again and do the environments tutorial. So any questions on that stuff before we begin? I guess ask in the chat and we'll get to it.
Now we're going to jump in and do a little bit of hands-on, create some environments, install some packages inside of our environments, etc. So again, you're going to need a virtual machine for this. If you guys logged off in the break, make sure to log back on. If you log back on, make sure to cd back into that Spack directory and resource this script, the setup env script, so that you have Spack in your path, so that if you run Spack, You're going to get an output rather than a command not found. If we do that, we're ready to start playing with and making some environments. As Todd mentioned, environments are really helpful for CI/CD systems. They're helpful to document your project. So you have this Spack YAML file, which is really a collection of all of the different specs, all of the different packages that you want to install and set up together. So to get started, we can run a Spack find here, see what we have on our local system. This is from me doing the GCC work earlier, so you can see that we have GCC 12 and a whole bunch of its dependencies installed. These are all installed outside of an environment in kind of this general space where we can install lots of packages. But we'll see that when we go and install packages, they're going to unify more nicely together. We also get a couple of benefits and can load them into our environment, so you can actually use them without having to use Spack load. So here, let's create an environment. We're going to do Spack env, which is short for environment, create, and we're going to create an environment called my project. And now we can see how, what you can create arbitrarily many environments. You can name them whatever you want. If you want to see the different environments that you have available, you can do a Spack env list. So this shows that we just have the one environment that we created called my project. We can now activate that environment with Spack env activate my project. And now if we run Spack env list, or ls for short again, you can see which environment you have active here because it's going to show up in green now. So now if we run that same Spack find from before, you're going to see that we get very different output. And this is really to say we've now jumped into, a little sandbox for ourselves. We can still reuse packages that we've installed globally, but this is going to track more of the specific packages that we have in this environment. In addition to Spack find, you can also use Spack env status, and this will show you the different packages once we've installed them into your environment. So now to, unactivate or deactivate an environment, we've got two ways of doing it. You can do Spack env deactivate, or we made a fun shorthand, as we like to make up words here on the Spack team. So you can do despacktivate. And now if you do Spack env status, you'll see that we don't have an active environment anymore. And if we go back and run that Spack find again, you're going to see that we have all of those packages like we had before. So let's jump back into the my project environment. So we'll do Spack env activate my project. And we wanted to see Spack env ls. You can see that we're now back into the project. And now let's try installing TCL, just like we did in the earlier tutorial. And you're going to see that this failed. And it's going to say, hey, I can't install TCL because it's not in the environment. So we break out the steps of installing a package into an environment from one install into what we call an add and an install. Add is going to add a package into your environment. So here we can do a Spack add TCL. And this is to say that you might be working in an environment and we really want to make the steps of importing a package into that environment, modifying that spack.yaml file explicit so that you don't accidentally go in and install packages into an environment that you didn't intend to. So now after we've done Spack add TCL, let's also add Trilinos. So we're going to do Spack add Trilinos. And now if we do a Spack find, we're going to see we've got two root specs. Neither of them are installed here, but they're now both in that environment. So now we can run Spack install, and we're not going to give it any arguments this time. We're just going to say Spack install, because if you're in an environment and you say just Spack install, it's going to install everything that you've asked for in that environment. So Spack add really plans. It says, hey, I want to add in a couple of different packages into my environment. And then you can Spack install, and it's going to unify the dependency trees across all of them if you ask for that in the configuration. We'll talk about that potentially a little bit later today, possibly tomorrow, definitely in the Stacks tutorial. But it's going to go in and it's going to then go install all of the packages that you need for that environment. So this is going to grab everything out of our binary cache, just like we were doing earlier with Trilinos, with TCL. And now if we run Spack find, a little bit prettier for folks. If we run a Spack find, you're going to see we're now showing up with those pluses showing something is installed, and here's all of the dependencies that got installed into our environment. If instead you really, you know what you're doing, you want to install something into an environment explicitly, you could say Spack install, when you're inside of an environment, you have an environment active, --add, and then you could do the same thing. You could say, I want to install both Trilinos and TCL into this environment in a single command. Now, we already have both of those installed, so we've gone ahead and done that. You can also break this out into, they can be two separate lines, or they could be on one line together. It doesn't matter for Spack. And now we'll go ahead and start, I guess, using some packages. So before, when we installed packages, they weren't automatically added to our path. But if you have an environment active, they will be. So we installed TCL. So here we're going to look for and say, where is TCL SH? So the TCL shell. And you can see that it was, or there's a symlink to the installation for us inside of a bin directory in our environment, and that is present in our path. So if we wanted to test, let's just see if this really, does this work? Yep, we can jump into TCL. We can write a tiny little hello world example, get some output, exit out of that shell. So environments are really nice for, grabbing a whole bunch of packages and then modifying your actual shell environment so you can use them just like native packages on a system. And now that we've installed some packages, let's uninstall some packages. So let's go ahead and create another environment here and talk about some processes here. So again, if we do a Spack env ls, you can see that we're in my project. If we do Spack env create, we're going to create on my project 2. And now if we do a Spack env ls, you'll see we've got two outputs here. If we do Spack env activate my project 2, and again run Spack env ls, now you'll see that we've jumped into my project 2, into the new environment that we just created. Inside of this environment, let's add two packages, scr and Trilinos. And again, let's run a Spack install after we've added those two packages. So this will go through, again, this is going to reuse packages that you've installed globally. So it's not like we're duplicating bits on the disk anywhere here, but it allows you to isolate and kind of partition different workspaces so that you can have different paths and different collections of packages present to users. So this is going to go ahead, it concretized Trilinos and SER. It's going to go grab them out of our mirror. And now, say, we want to uninstall Trilinos. We're kind of fickle, we just install it, but why not uninstall it? And if we do this, we're going to get an error here. And it says, hey, even though you want to uninstall Trilinos, it's used in another environment on your system. So Spack is keeping track of all of these packages and all of the environments that you've installed them into, and it's going to try and warn you from doing something dumb, like accidentally ripping out a package that you're using in another project. So if you had different environments for different, coding projects that you're working on or different experiments, Spack is going to say, hey, I was able to reuse this across multiple, but if you're trying to uninstall it from one, there are still others. You can overwrite this just like we talked about previously with uninstalling packages. So here, if we remove Trilinos, like if you no longer want Trilinos in your environment, but you do want to keep it installed because it's in another system, we'll just remove it from this environment. And after we do this, we can do a Spack find. You'll notice Trilinos is still in here. It's grayed out here because it's no longer explicitly installed in this environment, but it's still going to show up in your path until we reconcretize the environment. And so we can do that with the Spack concretize command. And Spack concretize is really a good way of saying if you've added a bunch of packages or removed packages, concretize is going to go reprocess the dependency tree for you and output, regenerate your paths, your views, do all of that work for you. So now if we were to run Spack find again, you'll see that it's now taken out. We no longer have a Trilinos in here, and it's simplified in our environment to just having the one SCR root Spack. It's updated that path and the bin directory that we saw when we used the TCL shell earlier. So let's jump back into that first environment that we created, where Trilinos is still installed. So we'll do Spack env activate my project. Let's do a Spack find inside of here. You can see we still have, even though we removed Trilinos from that other environment, it's still here. It's just fine. We've got TCL and Trilinos and all of their dependencies. So adding and removing packages lets you import and remove them from different environments, but it's not going to actually change the bits on the disk for what's installed or not. So let's jump into and look at this spack.yaml file. We've talked about it a little bit. A spack.yaml file is how you track your environment, and you can either add or modify packages through the command line, through Spack add, Spack remove, or you can do them by editing the package file and then reconcretizing. If we do a Spack config git here inside of this environment, you'll see we've got a lot of config in here, but the top level bit with actually in this environment for us that we're interested in is we've got two specs in this environment, Trilinos and TCL. We've also got view equals true. So I talked about that a little while ago. Inside of an environment, we generate views. These are really like file systems that you would see at the root of a lot of Linux distributions. So you've got a -bin, you've got a -share, and that is going to be all of the packages. We create symlinks and populate those directories so that you can link out to them as you would any other package installed on a system. And they're all living next to each other, so you can import one path into your shell and then have access to all of your packages. We'll talk in the stack section about what the concretizer unify true and false is. Todd just talked about reuse in the previous section on concepts. So we're reusing dependencies as much as possible here, but you could disable that if you wanted to. So let's jump in and we'll edit our config file for our Spack environment by running Spack config edit. And because I am workless in VI, I'm really quickly going to set my editor to Emacs. Okay, perfect. And so now you can see this is what we were just talking about before. You've got your two different specs. Inside of here, we are going to have it so that this environment builds using InPitch as our provided MPI rather than something like OpenMPI. So we're going to go ahead and add a section in here called packages. This is very similar to if you look at the main configuration of Spack, there's a packages inside of there, or a packages file. You can redefine basically any Spack configuration inside of environments that you would outside in your main Spack installation, so that when you share these environments with folks, they have the same configurations that you do. And here we're going to say that for MPI, we require our MPI provider to be InPitch when we build and use TCL and Trileos. So we went in, we added that. Now to have those changes be picked up in our environment, we're going to reconcretize. This time, though, we already have these packages installed, and they satisfy our requirements. So if we were just to run Spack concretize, Spack's going to come up with us or come back to us and say, hey, I've already installed everything you wanted. We have a concrete environment. So here we need to say --force or -f and say, I want to reconcretize the environment fully, given that I now have new constraints that I want to use InPitch rather than OpenMPI or another of the providers. And once we reconcretize this, we'll get a new TCL and a new Trileos, building on top of InPitch as our MPI provider. And you can see we're reusing most everything except for our top level Trileos needs to be installed again. And so we could come in here and do a new, we could come in here and then reconcretize and reinstall the environment and pick up our new version of Trileos and have a new, basically after you go modify your configuration, you want to always reconcretize so that you're picking up that new configuration. So let's say that we want to create a temporary environment. We want to do a couple of changes, or we want to do a couple of tests here. So we're going to do Spack env activate --temp. This creates a temporary environment. So we're no longer in my project or my project 2. And let's test and install here with Spack install add, and we're going to create a Python in here. So this is going to come in and generate us a Python, or generate us an environment that has and is reusing Python from our system. And let's say that we want to come in here and we want to install Python NumPy. So PyNumPy in the Spack, the Py prefix that we talked about a little bit earlier when we were looking at list. We're going to do that again. So Spack add PyNumPy. We're going to give it a specific version. We're going to come in here and we're going to concretize again. And when we do this, we're going to see that the Python that we originally picked up here, Python 3.11.7, is incompatible with the version of NumPy that we want to use. And so we're going to have to reinstall a different version of Python. And this is because when you're installing two packages inside of the same environment with unify set to true, we try not to install multiple versions of the same package, right? Because if you're generating a path and you have two Pythons in the same path, it would be a race condition for which one gets put into the path first, or, it would be kind of a mess one way or another. So you can see we did this again, and we were able to get a version of NumPy that we can use, but to do that, we have to pick a little bit of an older version of Python that is compatible with that version of NumPy. So that's just a little bit to talk about unify equals true. If you end up reconcretizing an environment and you see packages that previously you've installed get thrown out in the concretization, it's because Spack is trying to unify and make all of these packages work together. And so each package's constraints might affect another of your top level root specs. let's jump back into my project 2 here, and we'll talk about how we can build packages once we're inside of environments. Or we can build, our top level projects once we're inside of environments. So we'll do Spack env activate my project 2. We can do Spack env ls just to double check that. But as you can see, my project 2 is green. We've jumped out of that temporary environment that we had before. And if we just did which MPICC, this is going to show, hey, look, we have inside of our path that's in our system here, we've got an MPICC. So we could write a relatively simple MPI project on top of this MPICC, compile it and run it, which is kind of what we'll go ahead and do. Just to show how Spack is modifying our path here, we can look at our environment by running env, and then let's grep for just looking at our path there. You can see we get a couple of different ones. Spack is also going to modify your man path for you, your package config path, and then your main path, which is potentially the most interesting for us in the shell at the moment. And you can see that here we've prepended onto the system, such like user bin /bin, our environment path. So even if you have duplicates on the system, you're going to, because we're prepending, you're going to get the stuff from Spack first. So once you've activated an environment that has MPI in it, great, you've got MPICC in your path. Let's go write a simple MPI program. So let's create a file. You can do it in whatever text editor you like. I believe these VMs have VI, Emacs, Nano all installed. So I'm going to jump into Emacs because it's my editor of choice. And for the sake of time, I'm going to copy and paste this, but you can write, this is just a simple C program using MPI. We'll save this, and then we can use, just like you would any other version of MPICC that's installed on your system. We're going to run MPICC. We're going to compile our MPI Hello World program. And here, this MPI program is checking out your zlib version. And so we're going to have to tell MPICC where it can go and find the zlibng include file from. And so in the basic session, we also used Spack location. We're going to use it again here. And we're going to say, I want to include, coming from the zlibng package that I have installed in this environment, I want to include the include file into my MPI program. If we run this, we'll compile our program, and then we can run MPI run. Let's do 2 ranks, and we'll look at that output. And there you go. You can see hello world from both of the ranks of our little MPI program. And then you can see the version of zlibng that is found by the system is what we would expect by running Spack find inside of this environment, and then looking down at the zlib that we have installed here. Spack environments are also very handy for reproducibility. So if you're working on an experiment, you're publishing a paper, you can publish your Spack environment and allow collaborators to spin up the same set of packages in their environment that you have in yours. We can do this, there's 2 ways really of creating environments inside of Spack. The way that we've showed before, where you're doing Spack env create and the name of an env, or the name of an environment. We also have what we used to call autonomous environments. Now I believe that we're calling them independent environments. But this is really, you can create an environment in any directory, and then you can activate an environment from a directory. And this makes it really easy for you to put your environment inside of a Git repository and share it between, everyone on your team, and track all of the packages in Git so that you know when the environment's changed, when someone has added or updated a dependency, and you can track and rebuild that environment on your system so that you have consistency. So here, as we just talked about, your managed environments are when you do a Spack env create in the name of an environment. And then to create an environment inside of a directory, we're going to do Spack env create -d and the name of a directory. And then we will go in and we can run through, having your environment inside of your directory. If you want to go see the directory that contains a managed environment, you can do that too, just for either editing the files directly, or if you wanted to share them with someone, we can do Spack cd. So this is going to cd into, if we do -e in the name of environment, so my project for this case, this will cd us into the directory of our managed my project environment. And inside of here, you can see we've got our Spack YAML file and our Spack lock file. The YAML file is that abstract representation. It's the configuration that we gave by doing Spack config edit earlier. Spack lock is the concrete environment. So it's Spack saying, here are all of the dependencies that I installed and all of their exact versions. And so if you took a lock file, you can either create a new environment from the lock file, or if you take that same lock file somewhere, you can reproduce the exact same environment because it's got all of the exact versions in it rather than the abstract representation. So we talked about creating these managed environments. We're going to cd out of that space, and let's talk about creating an independent environment. So an environment that you would stick inside of a Git repository to share with some users. So let's create a code directory here, just as an example for some project that you're working on. We'll cd into code. And now inside of that directory, we'll run Spack env create -d. And then we're just going to create the environment in our current working directory. So here we can use a period. And now we've created our independent environment inside of username and that code directory. So if we ls here, you can see that we've got our Spack YAML file for our environment. And if we wanted to take a look at this file, if we just want to cat it out, it's what you would expect. It is, we haven't added any packages, or we haven't added any packages yet, but we've got our kind of basic configuration for defining the Spack environment. You can also see that if we did Spack env-ls again, this environment is not managed by Spack. It's not like internal to the Spack installation that you've created. It's external in this directory, so it's not going to show up in Spack env-ls. But nonetheless, it's still an environment that we can activate and use inside of this directory. So here, let's go edit the Spack YAML file. And let's go here and let's add 2 specs. We're going to add Trilinos. And we're going to add OpenMPI. So Spack files, this is basically doing the same thing as Spack add with these 2 packages. They're isomorphic, you could do either. But in this case, you can just edit the file and then let's activate our environment. So we'll jump into this environment by doing Spack env activate and then dot to say I want to activate the environment that is in this current directory. We could do a Spack find. And we can see that we've got our 2 root specs that we defined in the Spack YAML file, but we haven't installed anything yet. So let's go ahead and run Spack install. This will go and install OpenMPI for us and Trilinos on top of that. And once we've added all of these packages in, we can come in and we can add in our, we can add additional files, or we can add additional packages, excuse me. So in this case, we'll go ahead and add in. So now we've got our environment here. If we want to do Spack find again, you can see that we've got OpenMPI and Trilinos now installed. Let's add in HDF5 5.5.1 into this environment. So again, we could edit that file, or we could just type Spack add HDF5. at 5.5.1, and that'll add it to the environment. And if we take a look at that file again, you can see it's just appended HDF5 with our constraint as another one of the top level specs in our environment. Similarly, if you were to Spack remove HDF5 from our environment, and then if we wanted to go look at this file again, you can see really all that's happening is adding and removing from this list. So we're back down to just having Trilinos and OpenMPI. If you want to take a look at the Spack lock file, it is really a JSON encoded file. And so we can take a look at it by using the JQ tool, which we pre-installed on the virtual machines for everyone. So let's take a look at like the top 30 lines. That's going to be a really big file, but we'll take a look at the top 30 lines of our Spack lock file. So we can run JQ. We're going to load that from the Spack lock file. We're going to pipe the output of that to head and look at the first 30 lines. And so here you can see we've got a little bit of metadata about the lock file itself, what version it is, so that you can carry these forward over time, the commit of Spack or the release of Spack that generated this, and then our two top-level root specs. So we've got OpenMPI and Trilinos here, their hashes, and then all of the concrete specs of the environment would follow here. So this is going to be all the dependencies of OpenMPI, all the dependencies of Trilinos, and lots of information about them. So their hash, obviously, the name of the package, the version, the operating system that you're using to compile it. So on these VMs, we're using Linux, but you can install Spack on Mac OS and Windows. And then specifically the distribution here and our target architecture that we're compiling against. If we wanted to take this lock file and we can create new environments from either from our Spack YAML file or from our Spack lock file. So here, let's create a new environment, and we're going to call it abstract, just for fun. So Spack env create abstract. But previously, where we've just given the name of an environment and we started from a blank environment, this time we're going to give spack.yaml and say, I am importing from the environment that I have in this local directory that's got the file named spack.yaml. I'm going to import that as kind of the base, the start of my new environment. So now we've got our abstract environment. And if we do Spack env activate on this, so we'll activate our abstract environment. We can then do Spack find, and you'll see because we imported from the independent environment that we had in this working directory inside of our code directory that we created, we've got two root specs, OpenMPI and Trilinos. So this is a handy way for collaborators to say, here's my Spack YAML environment file, go create your own environments based off of this file. And build on top of them so that you can modify them if you didn't want to share them in a common directory. So here, we can also do this with a concrete environment. So instead of importing from our spack.yaml, our abstract representation of the environment, we can also use our lock file. So here we'll do Spack env create. We're going to create an environment called concrete this time. And instead of coming from Spack YAML like we did before, we're going to do Spack lock this time. And now if we jump into that environment, if we do Spack env activate concrete, and then we do a Spack find, you're going to see this is a little bit different in that it's come back and it's already got all of the installed specs. And this is because Spack is able to go and look up and say, okay, you're coming from a concrete or like a lock file. you want a concrete environment, but you should go check that you have all of these installed, and if not, install them and set up the environment such that it matches the Spack file. And that is, I think we finished, I guess, a little bit ahead of schedule. So we've got a little bit of time to talk about Spack configuration. But yeah, so we talked about creating environments, activating the environments to get the packages from the environments into your path so that you can use them for, tasks such as compiling an MPI program, compiling a C program, sharing environments as independent environments inside of directories like your code directory so that you can put your Spack log file and your Spack YAML into a repository and share them through Git. And then swapping between lots of different environments and keeping them all separate keeps your paths nice. So I'll go ahead and hand this off to Greg, and he can take a couple of minutes to start talking about Spack config, and then we'll continue that on tomorrow.
All right. So I'm moving on to the configuration section of the tutorial, and what I've got up so far is I've just followed the catch-up instructions from the top of the tutorial. So if you weren't following along with Alec, you may need that to get up to speed. So we're going to talk about Spack configuration. We've teased this a little bit in a few places, but we're going to talk about what some of the most important configuration options, but also some about just how the configuration system works. So the first thing that we're going to do is we're going to Spack config add concretizer :reuse :false. And that is going to update the default behavior of the concretizer to not do the reuse feature that Todd talked about earlier. And that's important because some of the preferences that we're going to configure in this tutorial are just a lot easier to see in the outputs when you're not using reuse, because the reuse will conflict with the preferences. And configuring Spack to prioritize these preferences over reuse is a little more complicated. So Spack has a lot of places that you can set configuration. The defaults come from the Spack root under etc Spack defaults, and these should be treated as read-only. There's no need to override them because the site config also goes in the Spack root and will be prioritized more highly. There are also a scope in /etc and the user config scope in your home directory. These are the primary configuration scopes. There is also the custom scope that you can add from the command line with the spack-c or --config scope argument. So spack-C. You can also put individual config items in that scope using the lowercase c. And then above that, anything in the spack.yaml from your environment is at the highest level. And then not really config that you can write, but some command line options come in as a config scope. So you could see this in an error output or something like that. For many of these scopes, they also have a platform-specific scope. So if we look at our ~/.spack directory, you can see by default we got a Linux scope, and compilers are the only config that by default goes in a platform-specific scope. So when we added a mirror, it created this file. When we did our Spack config add line a moment ago, it added this file. And we've got our compilers.yaml. The YAML format is normal plain YAML with one addition. And the addition is that you can have a double colon. So if you have an environment with a compiler section with a double colon, that means drop all of the lower priority configs before using this. So instead of merging the config, we're just taking this. So for example, here's the configuration you would give in an environment to say, here's a compiler that I want to use, and this is the only compiler that's allowed. Drop all the others. So now let's actually play around with the configuration. I am going to export my editor so that you don't have to watch me flail around in VI. And we're going to Spack config edit compilers. And here we see the same 3 compilers that we saw in the basics section through the Spack compiler list output. Now we're going to duplicate this first entry, and we're going to create a new compiler. We're going to call this clang at 14.0.0-G Fortran. In general, the compiler spec name has to be one of the known options that Spack understands. The version can be anything, but we're best off keeping the version version number as part of it, so that any version number comparisons evaluate the same, and suffixing if we want to change it. And we're just going to make a pretty common modification that people want. We want the Clang C and C++ compilers, but since Flang isn't really ready yet, we're going to use G Fortran. And that's the only change we're making here. So now let's try this out. We can Spack. I'm going to just clear to bring this to the top of the screen. We can Spack install -- no cache, says don't use any binary caches. We want to actually be testing the compiler. We'll build zlib since it builds quickly. And %clang at 14.0.0-G Fortran. And that'll build, and that'll test our compiler, except that it doesn't actually do any Fortran, right? Zlib is a C project. So the next thing we're going to do is we're going to install a CMake. Spack install --reuse. So this will override the option we gave earlier to turn off reuse. And we're going to say CMake %GCC at 11.4.0, just to make sure we're getting one from the cache. I'll even throw --cache only. And now we can build something that actually depends on Fortran. So we're going to tell it to build with the same CMake we just installed. Okay, so we can modify a compiler, give it a different name. We Spack config edit compilers. I saw someone was asking about this at equals versus just at. When you give a version with the at syntax in Spack, it is naturally a version range. Any compiler with any suffix on that version is the same. So clang at 14.0.0 is satisfied by a 14.0.0-.1. If you want to specify no, exactly this version, do not accept any suffixes to it, you throw the at syntax. So you can say, for example, if you wanted to use this compiler and not get the G4tran additions, you could say spack install zlib %clang at equals 14.0.0, and it would not consider this as a viable substitute for it. All right, so now let's play with some other fields. We're going to play with compiler flags a bit. So we're going to get rid of that empty list, and we're just going to say, set the CPP flags to -G. And now we don't need to install anything to test this at this point. We can say spack spec JSON Fortran %clang at 14.0.0-G4tran. It would help if I can type properly. And what we're going to see is that every compiler that uses, or every package that uses this compiler has these flags set as part of the spec. Pretty straightforward. There are a few other fields of the compiler configuration that we haven't talked about. The target is the CPU architecture family that the compiler builds for. So we are not going to get specific with this. It's not going to be as specific as a spec target, right? We see here x86-64b3, but rather we would just see x86-64 because it can target any architecture in that family. The modules field of the compiler was originally designed to support older Cray systems where the module system was the only way to access the compilers. But it's useful still on any system where you have a compiler that only works when a particular module is loaded. Any module that you list here is going to be loaded before Spack will ever invoke that compiler. The environment variable, the environment dictionary can also be used similarly if your compiler doesn't know where to find its own libraries and you need to set LD library path to be able to use the compiler. You can set it in here. It's also commonly used for licenses, or was commonly used with the older Intel compilers for license variables. Then the extra rpaths field is the last one we're going to talk about, and this allows you to automatically rpath a particular directory anytime you use this compiler. Again, this is a feature that we don't need to use as often as we used to. A lot of the compilers have gotten better about rpathing their own runtime libraries by default, and when you build a compiler with Spack, we will always try to configure it to do so. But some compilers aren't as good at this, and you can specify an additional directory to rpath in any executable using that compiler, just to make sure that it can find its runtime libraries. So that's it for configuring compilers for today. Any questions on that? If not, we will move on to configuring package preferences. So we're going to spack config -- scope defaults, edit packages. And here we're going to see the default configuration for package preferences. And we can see we got a question earlier about, do we build with GCC by default? Well, yes, by default, we're going to prefer GCC. And within each compiler, it's going to prefer the newest versions. Another way we can see the same information is we can say spack config blame packages. And we can see all of our package preferences Here's some things we set up for the tutorial to build for a generic target so that we didn't need to know about which sort of VMs we were going to land on. Here's all the defaults. And then here's a couple of Linux-specific defaults for Icon V. So we will spec HDF5. And unsurprisingly, what we're going to see is that the defaults will be respected. And by default, our MPI provider is going to be OpenMPI. And by default, we're going to build with the newest GCC that we have available. And that's what we get, right? We're building with GCC and using OpenMPI. So now let's create an environment. And there's an environment. And we don't need to do this in an environment. We're going to do it in an environment for the tutorial because it's then easier to make sure that we remove it at the end of this section, because the configuration that we're doing in this section would conflict with some of the later sections of the tutorial. So here's what we're going to do. We're going to say packages, all. We're going to override that compiler section. And if we leave something unmentioned here, that doesn't mean Spack can't use it. That just means we don't have any preferences among those, and Spack can do whatever it wants, which under the hood is going to be, it's going to go alphabetically beyond what we've specified. And then we can say providers. And here's the same thing. We're going to flip-flop the mpitch and OpenMPI, and anything else, we haven't specified a preference. And now we're going to see new default behavior. Spack's going to concretize to use mpitch, and it's going to concretize to use our new special clang, because that is the highest versioned clang that we have. Adding a suffix is a hair higher version. And there we've got our compiler flags that we configured earlier. We can also do variant preferences or requirements per package. So we can, if we spec config edit again to get this back, in addition to configuring things for all packages, we can say just for HDF5, and we could say prefer, or we can say require and give a spec that we require. Not all that surprising what this is going to do. It's going to turn off the MPI dependency. We're going to get a simpler spec. It's not going to change the compiler preference. Pretty straightforward. So now, the most important thing generally with managing Spack config ends up being external packages, because usually we end up having some packages from outside of Spack that we want to make use of. So we are going to Spack config edit again, and we're going to put in Perl. I'm going to create a list of externals. And I happen to know about the Perl on the system, that it's version 5.34.0. I could run, Perl -- version to check that out. And I know that the system compiler is GCC 11.4.0. And it's installed in /user. Now, if we spec HDF5 again, we are going to see instead of using a built Perl with all of its dependencies or installing a new one, we're going to get this external Perl. But interestingly, this overrode all of our compiler preferences. Because Spack saw we wanted to use this external Perl, and by default, Spack's going to try to keep us using the same compiler in the whole stack. So we can override that by saying build HDF5 with Clang. This isn't just a preference, this is a requirement. Now we could configure it as a requirement, or we can just stick it in our spec that we're requesting. And here we're going to run into something slightly subtle. Okay, it didn't use the external anymore because Spack tries to keep us using the same compiler everywhere. So how can we handle this? There's two things we could do. One, we could say, build me HDF5 with Clang, but build it with Perl built with GCC, caret Perl %GCC, and that would work. But really what we mean here is I want HDF5 built with Clang, and in my configuration, I have this external Perl, and Spack, you're not allowed to build any other Perls. You have to use this external. So you can set buildable false here. And with buildable false, now we've been specific enough with Spack that Spack's going to say, okay, what you've requested requires a mixture of compilers. That's fine, we can do that. And you get the external used here, but everything else built with Clang. I saw there's a question about where, how do you find where Perl is? In this case, we could run which Perl and see its user bin Perl. And the structure of a Unix prefix, right? Your executable comes under bin. The prefix is the parent directory to bin.
Most of the externals are doing prefix searches, although there are some packages that do other mechanisms, like for MPI.
Yeah. So now we're going to let Spack find an external for us, which we could have done for Perl. Perl does support it. Not all packages support this, but we can say Spack external find mpitch. And we see it added some new configuration to our environment. We're going to Spack config edit to look at our environment again, and here's our mpitch spec. Now, first of all, if we're going to build with mpitch, we probably don't want to be building HDF5 without MPI anymore, but that's pretty straightforward. But there's another subtlety here. So we went through this whole thing with forcing Spack to use the external Perl. But with MPI, it gets a little subtler, because if we just say mpitch is buildable false, Spack's going to say, that's fine, I can build with OpenMPI instead. And maybe that's what we want, but most of the time what we really want is we don't want any MPIs to be built by Spack if we're trying to force it to use this mpitch that we have on the system. So we can actually specify a virtual package here, right? We've seen a package, but we can also specify a virtual, and we can just say buildable false for all MPI packages. Now, if we spec HDF5% Clang, something really interesting happens. We get an HDF5 without MPI, even though that's not the default. Why is this? Well, HDF5 with MPI wasn't going to work. We can test this out. We can say HDF5% Clang plus MPI, and we can see what happens. And what's going to happen is we have forced Spack to use one particular MPI implementation that we found on our system. And it turns out that this MPI is actually not compatible. This MPitch implementation is not compatible with HDF5. You get a nice conflict error message with some source about why it's the case. And there's a few things we could do here. We could find a version of HDF5 that doesn't have this conflict and add it to Spack. We could find a different external MPI or install a different external MPI. Or we can give up and say, okay, fine, get rid of the buildable false. You can build your own MPIs. By default, if we run Spack external find, it's only going to search for some common build tools, basically. So we'll see what it finds on these systems, right? A bunch of kind of normal system stuff, some of the security libraries, and we can see those in our config now. There's also an option on the Spack external find to have all of those things configured as not buildable when they're put into the config.
Greg, just a heads up, it's 11:30.
Yeah. So the last thing in the packages config is that we can configure permissions on a per package basis. If we do a Spack config blame packages, type grep-10 permissions, we can see what the default permissions are. And you can also set group permissions on a per package basis. So now we are going to Spack env deactivate. That's very important, or the rest of the tutorial tomorrow won't work if we're in the same session, although logging off would accomplish the same thing. And we are also going to Spack config remove concretizer : reuse. So this add and remove capability is a nice way of editing the config, except that it doesn't have the same expressiveness as the full YAML. So often it's better to just edit the YAML, but for something really simple like a Boolean value, fine, we'll turn it on and off. There's a section here in the script about the high-level config. This is a file that lets us set where Spack installs things, where Spack does its builds to install from. A lot of other things in here, like the level of parallelism that Spack should use for its make invocations. We're not going to go over this because we're tight on time. But there's a lot of configuration options in Spack, and this is a place that you can start looking at it. But the other place to start looking at it is just Spack config blame and the name of any config section that you want to know about. So that's it for the config section today. If people have questions, I'm going to try not to keep us on here, but if you go into the tutorial channel on Slack, we'll keep answering questions. We're not, tied to the exact timing of the live session. We're going to start back up at 8 a.m. tomorrow morning Pacific time. And we're going to continue with writing our own packages, the stack section, which I've mentioned in answer to a couple of questions for how to configure a large system install, and then some sections on developer workflows and binary packaging. We've got all of that coming up tomorrow. with that, I think I'm done. Todd, was there anything you wanted to add before we sign off for the day?
No, just thanks everybody for coming out to the tutorial. It's great to see this many people here, and we will have more tomorrow. We are going to be available all day in the tutorial channel and on Spack Slack, so feel free to ask more questions if you have them. And I guess the only other thing is we're going to shut down the instances after this and restart them tomorrow for the tutorial. So we won't be able to keep those online for until tomorrow. So you can't reclaim the same instance. But we'll put up the VM spreadsheet again and hopefully get everyone big instances tomorrow so that they're not quite as laggy. So thanks, and see you all tomorrow.